Thanks again, Anna, and thanks everyone for coming. I hope I can make it interesting for you. I'm going to talk about black swans and seismic risk in megacities of Southeast Asia. I think most of you know that I work at Geoscience Australia as well as at RSES at ANU. I'm also an honorary professor at the Bandung Institute of Technology and have been working with them for quite a long time. So the talk will have somewhat of a focus on Indonesia, but I've tried to widen it a bit more to consider Southeast Asia more widely. Unfortunately, I did bring us back to the pandemic, Anna. I'm sorry about that, but it occurred to me that we've heard a lot about scientists. Scientists warning that the COVID-19 is an inevitable consequence of humans putting themselves into contact with nature in ways that have no precedent. And I got this quote from someone who had written about this: future pandemics are likely to happen more frequently, have greater economic impact, and kill more people if we are not extremely careful about the possible impacts of the choices we make today. And I think that you can apply this equally well to earthquakes, that we could equally warn that earthquake disasters are an inevitable consequence of humans putting themselves into vulnerable built environments in ways that have no precedent. And so there's another quote: future earthquakes disasters are likely to happen more frequently, have greater economic impact, and kill more people if we're not extremely careful about the possible impacts of the choices we make today. And that's a quote from me that I'm making right now. So you can see I only changed the one word, and I think it equally applies to earthquakes. So I think this is, this idea that, we have to be very careful about the decisions we make now applies to earthquakes and many other disasters, as well as the pandemic. And I think that the situation is changing. The reason we have to be very careful about these decisions is because of the rapid situation that's changing, especially with respect to urbanization in Southeast Asia. And this slide just illustrates the rise of megacities throughout the 20th and the first part of the 21st century. And this is causing problems for hazards and other earthquakes, because we're concentrating very large populations. You can see especially the growth of megacities in Southeast Asia, where large populations are getting concentrated in very small areas where they can be affected by even a relatively small footprint event. So for example, we saw the 2004 Indian Ocean earthquake. That was a large footprint event, killed many people, but you don't actually need such a massive earthquake, such a massive event, to kill a lot of people if they're all concentrated in one place. In addition, these people tend to be more vulnerable because in a highly urban area, the construction standards, at least in Southeast Asia especially, can be poor, and you get a much higher people per building ratio. And they also tend to be more dependent on critical lifelines like water, sanitation, and power. And also there tends to be, at least some people have pointed out, that there tends to be less social cohesion in urban environments. So the people are less likely to help each other, basically, and they don't have as strong a social network to get support when a disaster does affect them. I also wanted to make the point, I've used this slide in several talks in the past, of large versus deadly earthquakes. On the left here is a table of very large earthquakes, the largest earthquakes. I think it's the 10 largest earthquakes that have been recorded. And you can see their magnitudes, above 8.5, going up to 9.5, and the fatalities in the rightmost column. And that's juxtaposed with deadly earthquakes, the recent deadly earthquakes. And you can see the magnitudes of those aren't really that big. They're, the lowest magnitude is 6.3, the 2006 Java earthquake. But the fatality counts are high, and typically much higher than the really large earthquakes. And this is simply due to this footprint effect, the fact that these really large earthquakes occur in subduction zones. And by their nature, they are offshore. They're at least 100 or more kilometers away from population centers. So they're really not killing that many people. And the ones that do have high fatality counts in that left table are ones that have generated big tsunamis that killed people from the tsunamis, not the building collapse. So really, these really big earthquakes are in subduction zones, not very close to population centers where they can't collapse that many buildings. Whereas these moderate sized earthquakes can occur they'll occur inland on inland faults, and they can occur right in population centers. And generally all of those earthquakes there have occurred, have ruptured right into population centers. So an earthquake, the deadliness of an earthquake doesn't necessarily correlate with size. And I think we should keep that in mind in the rest of this talk. And this is a figure from a recent earthquake in the Philippines. Oh, I left off the date. I think it was about a year ago that a magnitude 6 earthquake occurred 80 kilometers from Manila. So it was quite far away and really caused only light shaking in Manila. But it caused this spectacular effect where you can see this pool just sloshing out of this roof, off this hotel roof. And so I've used this in a previous talk as an illustration of a spectacular illustration of matched resonance. And I'm going to talk about that later, how the seismic waves cause the basin to resonate. That resonant frequency equals the resonant frequency of the basin, the sedimentary basin. That is the geologic structure that this place is in. That matches the building and the pool water. So it's this matched resonance. But it's also an illustration of the point I was making at the beginning of the talk, that we're building things in environments that really we have no precedent for. And so earthquakes of this size would have occurred at that distance from Manila in the historic past. It's a tectonically active area. So we've gotten earthquakes of that size at those distances from Manila in the past. But the reason we didn't see this kind of thing, the reason we're surprised by it, is that we didn't have these tall buildings with rooftop pools in the past. So this came as a big surprise, I think, to everyone, but it really shouldn't be. We should be able to forecast this kind of effect. This also occurred in a much more tragic way in the recent earthquake in Palu in Sulawesi. And this just illustrates the setting of that earthquake. That on the left is the island of Sulawesi in Indonesia. And you can see its tectonic setting, in particular, Palu Koro Fault that separates some of the tectonic blocks that make up Indonesia. And you can see here some blowups of this. You can see this, it's very evident in the topography. It's a major fault. It has a high slip rate. We know that we've known for some time that it's associated with high hazard, and it runs right through Palu City. Palu City, population over 350 people, is right on the top of this fault, which has a high slip rate and major active fault. So clearly this is an area of we knew prior to 2018 that this was an area of high earthquake risk. Someone doesn't have their microphone muted, by the way, if you could just check that. And indeed, in 2018, there was a major earthquake, and it happened just north of Palu, and it ruptured for a couple hundred kilometers down into Palu City. So it was a major earthquake, caused a tsunami, and a lot of buildings collapsed. The other thing it did was cause this major liquefaction event. And this is, unfortunately, I can't turn off the volume of this video, or at least I can do that. So this is a cell phone video taken just after the shaking stopped. And what you'll see, if you look carefully there, you'll see that house in particular just sort of sailing along almost horizontally. It's just like a big bus. It's just moving along. And this was due to a very low angle landslide that was induced by liquefaction. So the ground shaking due to the earthquake caused the soil to liquefy and lose cohesion. And that then triggered this very large, very low angle landslide that killed many people. It was a really tragic event. It buried thousands of people in that city. We don't think it happened, at least on that scale, in the past. And that's because these landslides appear to have been triggered, or a primary cause of these landslides was irrigation in the Palu Valley. This was a new way that we learned humans can exacerbate earthquake hazard. We know that we can cause earthquake hazard by things like pumping wastewater into the ground. That's been seen to affect the stress on faults and induce earthquakes. We know that having artificial filling parts of a city, with artificially filled land can cause greater ground shaking. So that's two ways that we know humans can actually change the earthquake hazard. But another way appears to be using irrigation on gentle alluvial slopes. Because what this did in Palu It used to be a relatively dry area and in fact experienced famine in colonial times. And for that reason, the colonial authorities built this big aqueduct called the Gambasa Aqueduct that you can see up here. And what this did, together with the irrigation of the rice paddies in the Pali Valley, raised the water table and brought that water table up right near the surface where it could, where it soaked, it caused these alluvial soil to be waterlogged, and that made it prone to liquefaction. So when the earthquake occurred, it did liquefy, lost its cohesion, and was able to fail in these really low angle landslides. Those angles are there. It's less than, the slopes are less than 2 degrees. So it's just remarkable that you would get a landslide at all on that kind of slope. Not to mention the fact that it would be these massive landslides that occurred. So, so the point I'm trying to make is that again, we have altered the landscape. This is unprecedented in this area. We didn't have a high water table, so we never had this before. But humans have now come in, altered the landscape, and made this area prone to liquefaction. Now, so we've had several black swan events in the Asia Pacific. I would say Palu would qualify as one of them, but the other big ones are the 2004 Indian Ocean tsunami and the 2011 Japan earthquake and tsunami. These events were much bigger than anyone had anticipated for those areas. And so I just posed the question, there is a 1 million fatality earthquake in Asia sometime in the 21st century, all but inevitable. We'll see if we can come back to that at the end of the talk. And I wanted to illustrate that to understand these black swan events, we really have to look at the way we thought about earthquakes. And so on the left here, this is probably the most technical slide in my talk, I think. On the left here is a figure that's just a textbook from a seismology textbook, very well-known figure by some seismologist named Prof and Kanamori, published from a paper published in 1980. And what it shows is earthquakes plotted against two fundamental tectonic parameters of subduction zones. Because as we discussed, the largest earthquakes occurred in subduction zones. And these guys were asking the question, well, why do we get these really large earthquakes above magnitude 8.5 in some subduction zones and not in others? So they just plotted them against some basic, very fundamental tectonic parameters. One is the plate convergence rate. These plates are coming together as illustrated in the upper right there. And here on the y-axis here, we go from very slow to very fast convergence rate. And then on the x-axis, we go from very old subducting plate, the geologic age of the subducting plate is quite old on the left, and it gets quite young on the right. And if you plot up the earthquakes on that, they're colored so that the red ones are the really big ones, the really big dangerous ones, shallow and very large. They all plot in the upper right. So from this, we could conclude, or we thought we could conclude, that these really large earthquakes will only happen in subduction zones that converge quickly, have relatively fast convergence rates, where a young plate is subducting. And there were various reasons why that made a lot of sense. People could explain that in terms of the frictional properties of the plate boundary. And it all made great sense until actually sometime just before the 2004 Indian Ocean tsunami, Stein and O'Call were reworking this. And they had found that there were better measurements of the convergence rates and the plate age. New earthquakes had occurred, and old earthquakes have been added to the record through historical analyses and paleoseismic studies. And this plot that we see over here on the left became this plot that we see over here on the right. And we can see that we no longer have this nice correlation where all the really dangerous large earthquakes occurred in the upper right. They're now much more scattered around. And in fact, after this paper was published, 2 earthquakes that had occurred, which makes them even more scattered. So we really don't, this correlation that we saw, this correlation that we thought allowed us to say where big earthquakes occurred and where they wouldn't, was really just wishful thinking on our part. There really wasn't any such correlation. And in retrospect, what probably happened, at least with respect to convergence rate, is that the rapid convergence rate meant that the earthquakes occur with more frequency, and we were more likely to have experienced them. But if we just wait longer, we'll find that the earthquakes with a less frequent occurrence will happen, and we'll see that in fact they do happen at very slowly converging subduction zones as well as fast converging subduction zone. So we were completely wrong, and we were wrong to base our hypothesis on the historical experience of earthquakes. This one case in point then is if you go just north of where the 2004 earthquake ruptured and look in the Bay of Bengal. And it turns out there we do have some sparse historical accounts that document an earthquake that occurred in 1762. And I worked on this back in 2007 and made the point that, you know, this was a very large earthquake. It very likely generated at least a local tsunami. It had major effects in Chittagong and the northern Bay of Bengal. And of course, having occurred once, it is likely that it will occur again. And this was rather, you know, it was a bit, it was difficult to have confidence in the very sparse historical accounts. So the paper was somewhat speculative about the actual size of the earthquake. But since then, a number of studies have been done, and I'm just going to show this one by someone named Hannah Booth in 2013, in which they studied, they looked at old kilns. There are big kilns in that area and the very northern tip of the Bay of Bengal, used for making salt, for evaporating the seawater and making salt. And these have been around for quite a long time. And in fact, if you dug down, you found that they had been buried. There were older kilns beneath them. And these guys did looked at these, they dug down, looked at these ancient kilns and did carbon dating and found that in fact there had been a catastrophic event. There appeared to have been a catastrophic event that occurred right at the end of the 1700s, possibly coinciding with the 1762 event, but in any case indicating that the only explanation they could have for this very rapid subsidence was tectonic activity. So it does seem like large earthquakes do indeed occur in this part of the Bay of Bengal. Now, at the time, that area, the northern tip of the Bay of Bengal, was relatively sparsely populated. It was really wilderness up there. But since then, it's been, this is partly due to the British colonial authorities trying to settle this area and promote agriculture. It's now densely populated. It's home to around 4 million people in this Ganges, Brahmaputra, Meghna Delta area. And many of these people live in villages in the outer delta area where they've had to build up embankments around the islands because of the sea level rise, well, not sea level rise, but because of cyclones and storm surges, you know, and even spring tides. They've built up these embankments, and once they do that, that will stop replenishment of the ground level through sediment input. And so that'll start to sink more, and they have to build up their embankments higher. And what you end up with are these kind of polder type settlements that you see on the left here, where you see these houses are on land that is well below the level of the sea. And you can see this also in this diagram to the right here, that they're about 1 meter below mean sea level. And so clearly this kind of structure, this kind of arrangement is very vulnerable to an earthquake or tsunami. Even a moderate tsunami, if it tops that embankment, poses the risk of catastrophic failure, or an earthquake shaking could potentially result in catastrophic failure of this embankment. So again, we have a situation where humans have created an environment that's very vulnerable to earthquakes without really understanding what the earthquake danger is. So this is an area where if we go far enough back in time, we can see, in fact, it could experience large earthquakes, and one should be very careful about, you know, building a kind of arrangement like this where you're protected by this relatively flimsy embankment. But, you know, we're now sort of stuck with this situation because of the decisions we made. All right, so I'll leave those, and now I'll start talking about megacities. This talk has megacities in the title, so that's what I should talk about. And I wanted to start with Dhaka. If we go even farther north from that Arakan coast that I just talked about, through Bangladesh, that the plate boundary between the India and Burma microplate cuts through Bangladesh and skirts the city of Dhaka. Which is the world's 9th largest city, 6th most densely populated, about 21 million people in the greater Dhaka area. It's grown very rapidly. It basically doubles the population, that is, doubles every 15 years, making it the world's fastest growing city, or at least that the World Bank said it was in 2015. But construction standards are poor. And in fact, they can be so poor that buildings are known to collapse spontaneously. This is the most well-known example. In 2013, a garment factory in Dhaka collapsed. It killed a number of workers, but it was just spontaneous. There was no earthquake, no event in particular. It just fell apart. So construction standards in Dhaka can be very poor. What about the earthquake risk? Well, in 2014, the project called the Bangladesh Urban Resilience Project, I think it's Urban Earthquake Resilience, sorry, I left that off, project, undertook a scenario-based seismic risk assessment. And they looked at several scenarios based on historical earthquake occurrence, and you can see those in the left here. There's Dhaka is there where the little star is, and there were couple of earthquakes that their scenarios resemble historical earthquakes occurrence. They include the 1762 that I had just discussed, and then the possibility of very large, pre-1500 earthquakes occurring farther up the plate boundary here. And their results were that for this magnitude 7.5 that possibly might occur on the Madhupur fault, you could get estimated fatalities of 40,000 to 150,000 for the Dhaka city region alone. So that's within the city limits, not greater Dhaka. So, it's a very, very high impact event. Very high fatalities would be possible for that. Since that study was done, there was another study by Steckler et al. In 2016. They used GPS measurements of crustal strain. So they're measuring the movement of the ground, the deformation of the ground that indicates that strain is building up in that region. And they concluded that there is in fact a very wide, potentially seismogenic zone right underneath Dhaka and to the east. And this area that's building up the strain energy is large enough to accommodate a very large earthquake of magnitude 8.2 to 9. And they just looked at the number of people that live within 100 kilometers of that source zone. It's a very large source zone. Bangladesh isn't all that big. There are lots of people that live there. There are 150 million people that live within 100 kilometers of this source zone. So were that to rupture in a single large event, it could affect a very, very large number of people. I want to move on then to Manila in the Philippines. Manila is surrounded on the east and west by subduction zones that pose a significant megathrust earthquake and tsunami hazard to the Philippines, but it also has this Philippines fault system that cuts through the Philippine islands themselves. And part of that, a spur of that fault system is a fault called the West Valley Fault, and that runs right through the heart of Manila. Manila is a megacity. It's grown by almost a factor of 10 between 1950 and 2020, from 1.5 to 13.9 million. And that's just the city population. The urban agglomeration, the whole area of Manila, the urban extent of Manila, including what's called Metro Manila, has a total population of 24 million people. So it's a huge, huge city with a big fault running right through it, basically. Oops, sorry. And this fault, it's only experienced one small earthquake, one tiny earthquake has been recorded on that fault. However, paleoseismic studies where geologists trench the fault and look for the evidence of past, including prehistoric earthquakes, find at least 3 or 4 surface rupturing events that have occurred in the past 1,400 years. So that suggests a recurrence interval of less than 500 years, meaning one is, could happen at any time, with a maximum magnitude as large as 7.2. So that's a big earthquake if to occur in an urban area. It might not be as big as some of the large subduction zone earthquakes that I've talked about earlier, but it's certainly large enough to cause many, many casualties in Manila. In 2013, Geoscience Australia, that is, worked with the Philippine Institute of Volcanology to do a risk assessment that it was focused on Quezon City, which is sort of part of the urban agglomeration of Manila, and with a population of 3 million people. And based on that earthquake, the results of the estimate of the earthquake impacts were 23,000 injuries and 5,500 fatalities. So quite a large impact. And if that's extrapolated to the rest of Manila, to Greater Manila, it will be several times larger. We don't know exactly how much larger, but it'll certainly be quite a bit larger than 5,500. And then finally, I want to go to Jakarta. I'll spend a bit more time on Jakarta, since I do a lot of my work there. The city of Jakarta has a population of 10 million, but again, Greater Jakarta, including the whole urban agglomeration that surrounds Jakarta, is 30 million, making it the world's second largest megacity. It lies about 300 kilometers from the Java Trench subduction zone, so the Australian plate is pushing underneath the Eurasian plate beneath Java, and it does that at about 6 centimeters per year. So that's a fairly rapid convergence rate for a subduction zone. It's also close, though, to several large and possibly active faults, and lies above a very active Benioff zone. Benioff zone is what we call the zone of active earthquakes that occur in the plate that is diving beneath Java. So those earthquakes could occur anywhere from, say, 70 to 200 kilometers depth, and they can be quite large. They can be up to magnitude 8, as I'll discuss. There have been, if you talk to people now who live in Jakarta, they typically say that Jakarta doesn't get big earthquakes, or doesn't really experience, doesn't experience large earthquakes. They haven't experienced in their living memory, nor have their parents or grandparents. But in colonial times, in the 18th and 19th century, it did experience a number of large earthquakes. There was a really big one in 1699, one in 1780, and another in 1834. And we did some work on this. This was published by Jonathan Griffin in BSSA to try to identify the sources of these earthquakes. It's very difficult just based on the historical accounts. But the conclusion was that 1699 was probably due to an intraslab earthquake, a very large intraslab earthquake. So that's in the plate that's pushing underneath Java, and it was about 100 to 150, about 100 kilometers deep beneath Jakarta. And then the others were due to crustal faults that are nearby. We did a similar earthquake risk assessment for Jakarta. Geoscience Australia worked with Indonesia's geological agency and their agency for meteorology, climatology, and geophysics, better known as BMKG. We did an earthquake assessment for Jakarta. We based it on the scenario for the 1699 earthquake, the one I just mentioned, being the magnitude 8 intraslab earthquake directly beneath Jakarta. And that hits Jakarta with very high shaking intensity, MMI 9 throughout the whole Jakarta area. And we estimated the fatalities of that would be 100,000 to 1 million people. So huge range there, obviously. Because there's lots of uncertainty involved in that, both on the ground motion estimate as well as on the effects on people. But so there's very large uncertainty, but clearly a very high fatality rate for that earthquake. So another big danger area. One thing that we don't take into account in those kind of scenario risk assessments is the potential for the basin response to enhance the impact. And that happens because when the waves go from a hard rock to the soft rock, they will increase in intensity just due to the sort of the physical boundary condition there. But it also happens because the waves sort of get trapped. They do get trapped in that sedimentary layer. They'll tend to bounce around, they'll reflect up and down within that sedimentary layer, and through a phenomenon known as constructive interference among the reflected waves, there'll be much greater enhancement at some periods as opposed to others. So at certain periods, you'll get really strong ground motion, and at others, it won't be that strong. This was an effect seen in Mexico City in 1985. This is sort of the classic example of this basin resonant effect when they had a big earthquake offshore. You can see there, here's the subduction zone off here, and you can see Mexico City quite a long distance away, 400 kilometers away. And these are some of the ground motion records from that earthquake, and you can see that very high ground motion near the epicenter of the earthquake, as you would expect, but it rapidly diminishes as you get away from the earthquake, as you move inland, much less ground motion. As I discussed, you know, these earthquakes, once they occur at 100, 200 kilometers distance, you don't have nearly as big an impact. The problem with Mexico City is it lies in this soft sedimentary basin here. And so if you look at those ground motion records, you see that they as soon as you enter the basin, they start to get much bigger. And in fact, for this station that's right in the basin, the ground motions, the peak acceleration that is as high as it is near the epicenter. And you'll notice though that the amplitude of that might be similar to this record, but the frequency content is much different. And you can see it's sort of ringing at a particular period. And in fact, the Mexico City basin resonates at about 1 to 2 second period. This could have an effect on buildings between 6 and 16 stories, which through a process which I'll discuss in a minute. And this led to a large number of deaths in this earthquake, 8,000 deaths with 500 buildings destroyed. And they were in that, generally most of the buildings were in that 6 to 16 story range. That's happening through this phenomenon that I mentioned at the beginning of the talk of matched resonance. The basin itself resonates through just due to the geology at 1 to 2 seconds period. So but the buildings also will have their own resonant frequency. They'll tend to want to move at a certain frequency. And you can think about that by thinking about when you were a kid and you were on a swing and you tried to get the swing moving, you know, at a really great height. And you would have found that if you swung at a certain period, at just the right period, you could really get that swing going back and forth really well. And that in other periods, if you went too fast or too slow, it wouldn't move that much. And that's exactly the same thing happens with buildings. Well, essentially the same thing happens with buildings. You can see here a tall building that moves back and forth, much as the swings back and forth. It does have different modes of vibration. Usually we regard the simplest mode of just sort of swinging back and forth as the most important. It's called the fundamental mode. And if we look at the fundamental mode of various bits and buildings, we see that office equipment might have a very short period, a 0.05 seconds period. A one-story building has about 0.1 second resonance period. And then as you get up into higher buildings, 10 to 20 stories, 1 to 2 seconds, and then 7 seconds for a 60-story building. So the bigger the building, the longer its resonant period. And you can see that 10 to 20 stories is about 1 to 2 seconds. So that corresponds to the resonant period of the Mexico City sedimentary basin. And that's why buildings in that height generally were the ones that collapsed and killed many people. Could this happen else? Oh, well, sorry. I wanted to show that this did happen. There was a spectacular example of this in the 2017 Mexico City earthquake. This was one of these intraslab earthquakes like we're talking about for Jakarta. It was a 7.1 near Mexico City. Watch that building in the background there. If you look very carefully, you can see the curtain swaying at about 1 to 2 second period. And if you can also see relative to that bush in front of the building is moving slightly until it eventually undergoes complete collapse. So this has been forced to resonate at its resonant period. The building's resonant period matches that of the sedimentary basin. This has resulted in large displacements in that fundamental mode and eventually complete collapse of that building. So in this case, there were over 200 fatalities and 44 buildings that collapsed. Could a similar thing happen to Jakarta and other megacities in Southeast Asia? Well, almost certainly it could. We wanted to look at this for Jakarta. Jakarta is, it's at a place where 3 rivers are flowing northward from the hills just south of Jakarta. They're flowing into the Java Sea at Jakarta Bay. And so there's a lot of very soft sediments basically that underlie Jakarta. It's been well known for a long time that those are relatively soft and extend for considerable depth. So we wanted to see, well, just how deep do they extend and what are the resonant periods they might excite? So to make a long story short, we looked at those resonant periods. I won't go into the type of analysis, but this is frequency here of the x-axis, and this is a measure of the resonant response of the sedimentary basin here. And you can see there are often the records exhibit two resonant peaks, one at relatively long period, about 5 or 6 seconds, which could potentially affect high-rise buildings in Jakarta, and then another at a few tens of seconds period, which could affect more low-rise residential structures. So both of those potentially are at risk due to these basin resonance effects. Now, it is possible to design, let me see, I can't do this. It is possible to design buildings to deal with these effects. Here we have an example of base isolation. On the left is a demonstration of base isolation where one of those buildings is attached to a table that's being shaken back and forth. The other has been base isolated. So it's got these at least in the real case, you have rubber plates that allow the building to sort of slide above the rapid motion of the shake table. And you can see that it undergoes a much more gentle rocking motion than the one that's directly attached. These are buildings in Tokyo in the 2011 Tokyo earthquake. And you can see, if you look carefully at cell phone footage, I'll play it again, you can see them sort of swaying gently back and forth. So it is possible to engineer buildings to withstand considerable displacement at long periods. But it does take some care, and you have to be aware of the need to do it. So in Japan, this is a fairly common practice to do with high-rise buildings. In Jakarta, there's only one building so far that's base isolated. So is this really a problem for Jakarta and other megacities in Southeast Asia? Most of my engineering colleagues don't like to think about the idea that a high-rise could collapse. They are built. All of them are built to international standards. They're built to withstand wind loads, and that usually makes them pretty resilient to any seismic shaking. However, if we were to worry about the buildings, particularly in Jakarta, experiencing damage due to this kind of phenomenon, we wouldn't be alone. Even in California, where building codes are rigorous and they are rigorously enforced, they're worried that they've gone too far and made buildings that are too high for a city in an earthquake zone. So I do think it's something that should be considered. Are these high buildings in places like Jakarta at risk? We need to understand to answer that kind of question, and also to understand the impacts on even lower rise structures where the bulk of the fatalities will occur. We really need to understand building behavior, and we need to understand how fragile some of these buildings are. And we really should do that by looking at actual earthquake damage. This was work done by one of my students, Muriel Neguit, following the 2013 Bohol earthquake in the Philippines. That caused a lot of damage in the small island of Bohol, and she was able to go in and do a building survey that tried to really measure how fragile some of those buildings were. And you can see she developed what are called fragility functions, which show that some buildings exceed their will experience high damage at they'll experience high damage at high intensity. This is intensity on that left axis here. Other buildings will not experience as much damage. And so that, given a model of this building fragility that shows that as the intensity increases here, the fragility of that building, or the damage that will be experienced by that building, goes up, we can then forecast what kind of damage will occur. And we can therefore look at the different building types and even look at changes to building types to try to determine how we can best build buildings to withstand an acceptable level of risk during earthquakes, or an acceptable level of shaking during earthquakes. This is really important to do in places like Indonesia, as well as elsewhere in Southeast Asia, because they are built to questionable standards, shall we say. The traditional construction in Java, as well as elsewhere in Asia, as I'll indicate in the next slide, is of wood construction. And that is actually quite resilient to earthquakes. And in fact, some of the features, the architectural features of the traditional wood construction are very well suited to withstand large displacements that might be experienced in an earthquake. But unfortunately, throughout the 20th century, these have largely been abandoned in favor of non-engineered construction using masonry, which is not a very earthquake resilient structure. That's illustrated in the lower right here. There's a brick building. That particular one has no reinforcement whatsoever. So it's a big problem then that you know, we appear to have many fragile buildings that are currently being built. They've been built through the latter part of the 20th century and are still being built now. And we really don't understand how fragile some of those are. Not only because it's brick, but because of the way the buildings are built and the quality of materials used. This is not only a problem in Indonesia. I want to include this slide. This is from some work by Roger Billam in Kashmir in Pakistan, in which he also shows that a traditional wood structure built in Kashmir, and includes a quote by someone from the 16th century who says, on account of the abundance of wood and the constant earthquakes, houses of stone and brick are not built. So they understood this problem even then, and they understood that wood was more resilient to seismic shaking. But unfortunately, you know, due to the difficulty in obtaining wood and just the rapid pace of construction, these have largely been abandoned in favor of, as to quote from Roger's paper, a ramshackle hodgepodge of masonry buildings with little resistance to ground shaking. So this is going from Pakistan all the way to Indonesia. I think it's a very prevalent problem throughout the whole South and Southeast Asia region, that we have building construction done with masonry structures that are not very resilient to earthquake shaking. In particular, in Indonesia, you can see this if you visit earthquake damaged areas. Just look, I'm not an engineer, I'm not an expert at this, but just looking at some of the earthquake damage tells me that there are really big problems, particularly seeing things like this reinforcing mesh with little bits of concrete still clinging to it shows me that, in fact, this concrete was of very poor quality. That's not the way concrete reinforcement is supposed to work. Reinforced concrete's a very good material. It's actually, unlike brick, it is actually very resilient and very strong to seismic shaking, but not if the concrete is really poor and does not adhere. It is supposed to adhere to the metal reinforcement, and that's what makes it so resilient and gives it its strength. If the concrete is poor and doesn't adhere, it will just crumble away, as you can see in these structures. If we look at, here's a photo from the California Northridge earthquake, which was a big earthquake, occurred right underneath LA, and subjected buildings to very intense loading. So this building did fail, but you can see that the failure is such that the concrete and the steel deformed as a unit. And so it took a lot of shaking to force this structure to fail the way it did. And when it did fail, it failed in such a way that if people were trapped in there at the time, they might have been able to escape. It didn't just completely crumble and collapse on top of people. It failed in a way that it hopefully preserved some life safety, and people were able to escape. That's the way concrete is supposed to fail, but typically you see it failing in this way in places in Indonesia, and I would hazard a guess elsewhere in Southeast Asia. So what do they do? What do you do? Do they all have to build the type of reinforced concrete structures that we see in California? This would obviously be too expensive for many developing countries in Southeast Asia. But there are a number of ways that have been worked out to try to develop retrofits, you know, trying to adapt existing structures that are not all that expensive. I won't go into these. This is just from a paper by the author mentioned in the lower right there, in which they used, you know, various kinds of meshes to try and reinforce the construction. But I would also emphasize that really just looking at basic things like the quality of concrete and the detail of reinforcing would go a long way towards reducing earthquake fatalities, or at least they would, I think they could save many lives in Southeast Asia if we were able to convince people to use them. Okay, so I'm finishing up. I've only got about 10 minutes left. My conclusions are actually very simple, but I will spend a little bit of time on them. Regardless of how likely a massive fatality earthquake in Southeast Asia is, we should recognize the possibility that such an event will occur. That might sound like a very obvious thing to say, but actually, it's very difficult to recognize that possibility. I have been involved in some of these seismic risk assessments, and you may have noticed when I talked about them, when I reviewed them, for example, the Dhaka seismic risk assessment only considered the smallest earthquake among their scenarios. They only listed fatality estimates for the smallest earthquake. And for the Manila earthquake, they only talked about Quezon City. And you might wonder why. And certainly when we did the Jakarta scenario impact study, we came up with those very high fatality numbers, but not everyone liked to hear that. People, both the scientists that are involved in this, because they don't want to sound alarmist, they don't like talking about 100,000 or let alone 1 million fatalities. Then of course, disaster managers who are looking for scenarios to test their response capability, they don't want to talk about dealing with 100,000 to 1 million fatalities, and understandably, because it will overwhelm the typical disaster response capability available in developing countries of Southeast Asia. But nevertheless, we really have to recognize that. I mean, even if we say, look, that's very unlikely, we're not going to plan for that, we should have it part of the discussion and make that decision explicitly and understand what kind of risk we're talking about taking on when we make that decision. Currently, we're making that decision by default. If we refuse to recognize this possibility, we're saying that we're just going to take the chance, build these flimsy buildings, and accept the risk that we're going to experience massive fatality earthquakes in the future. That might be okay, but we should at least do it. We should at least have it part of the discussion and have everyone aware that we're taking on that kind of risk. How would we prepare? Well, obviously, better disaster response planning is one way, and that would mean including these scenarios. We've had these kind of events in the past. Haiti was more than 200,000 deaths. The Indian Ocean tsunami was more than 200,000 deaths. So we know these things can happen, and I can understand the feeling for a disaster manager when he says, "Look, I just can't. We could never handle that. I just can't consider that." But they do happen, and we really should be trying to consider what we will do in the event of one of these massive impact earthquakes. The other thing in the long term is to promote better building practice. This is always the seismologist's response to how do we prepare, because the saying is that buildings kill people, earthquakes don't kill people, buildings kill people. And we need to have, that's the approach, the approach that has consistently worked in reducing earthquake fatalities is better building practice. So, and we need to do that because we need to prevent this lock-in of the fragile building stock that is occurring as we speak. These are the decisions that we are making now that are guaranteeing the inevitability of a major earthquake disaster. Now, in a developed country, what we would do is have a rigorous building code that we would rigorously enforce. And that has been shown to work in developed countries. Will that work? Can you do that in Southeast Asian countries where they simply don't have the means to build often to a building code? I've worked for over 10 years now in Indonesia trying to improve their seismic hazard map, which will support the building code, but the building code isn't applied to buildings less than 8 floors. So you have to wonder, well, what use was the hazard map in the building code if it's not applied? And to some extent, well, one approach would be to apply the building code and force people to follow it. But the other approach would be to take a simpler approach and just get people to adopt minimum requirements for strength and the detailing of reinforcement. Most of the houses are built with confined masonry and have some amount of reinforced concrete. And if they simply used some minimum strength of the concrete and proper detailing of the reinforcement, which should not be all that costly, I think has the potential to save many lives in future earthquake events. Hopefully someday we'll get to the point that we will have good hazard maps, good building codes, and proper enforcement. But in the meantime, I think the least we can do is have some very basic minimum requirements for earthquake strength. Because currently, I think it's simply not